I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. You guys are doing a great job on the assignments. I'm very impressed. One thing I want to point out, I think from an earlier assignment, that the correlation between two variables is a sample statistic. So a lot of times we start off with the sample statistics of if you have a categorical variable, the sample statistic is the proportion. And if you have a quantitative variable, the sample statistic is a mean, but there's other sample statistics. So sample statistics is just a general term for ways of measuring the data. Can anyone think of other sample statistics that we've used? So sample statistics is just taking the data and getting a specific type of value that you're going to then do a hypothesis. What is sample? Statistic? For me at least, the word statistic is like so general. It's like that's the name of this class, but what is statistic? And what it is just basically a value. You have a sample statistic, so it's a value generated from your sample, and then you have something called a population parameter, and that's a value generated from your population. I know it's not wonderfully intuitive, but at least what I've tried to do throughout this course is stay consistent. I'm very intentional of saying sample statistics, so you know I'm interested in values within the sample in a particular value, like the mean or the proportion or the correlation. Can anyone think of any other sample statistics that we've used when we do hypothesis testing? For gender and divorce, what did you guys use for your observed mean? It could be. So a sample statistic isn't just mean or proportion. Those are kind of like the foundation of sample statistics, but another sample statistic would be the proportion of females who get divorced minus the proportion of males who get divorced. And so from your sample, you can calculate this and you'll have a value. And so that's what we would call an observed sample statistic. So just like correlation is a sample statistic, other ones would be the difference in means, like the mean number of males minus the mean number of females. I bring this up because it'll continue to come up in this course, and the term will always be, what's your sample statistic? What's the observed sample statistic that you're interested in measuring? And so like with the gender and sex one, we were interested in knowing, is the proportion of females who get divorced greater than the proportion of males who get divorced? That's the statistic that she's wanting to measure. So to show how correlation is a sample statistic, it says, if we're testing to see if there's a correlation between height and salary, would that be a left tail, a right tail, or a two-tail test? If we're going to set up the hypothesis test for this, what would the null hypothesis be? The null hypothesis is always the claim that there is what? Chelsea?
There is no effect.
Okay, so the null hypothesis is always that there's no effect, there's no difference, there's no relationship, there's nothing going on there. So, okay, here's another thing. The null hypothesis is there is no correlation between height and salary. The way you would write the sample statistic for that, does someone want to take a stab at how you would write the equation part of that? What Chelsea just said, that there is no correlation between height and salary. What type of variables are height and salary? Quantitative. So then, because we're talking about the sample statistic of correlation, do you guys remember what the population parameter for correlation is? The symbol for correlation, do you guys know what that is?
Little r.
Little r. Okay, that's for the sample, so that's good. And then what is it for the population? It's called rho, which is Greek for big R. We're looking at correlation, and we want to say the correlation between height and salary. If Chelsea said there is no correlation between height and salary, this is our null hypothesis, what would this value be right here if there is no correlation between height and salary? And it'd be 0. And then can someone take a stab at what the alternative hypothesis?
There's a direct correlation between height and salary.
Okay, and so direct, does that mean positive or negative?
Neither.
Okay, so you're saying that there's a correlation between height and salary. And we don't actually know. It might be shorter people. It might be a negative correlation or a positive correlation. So here's the alternative hypothesis. We're claiming that there's a correlation between height and salary. That's all we're claiming. We're not even claiming a direction. We're saying that the correlation does not equal 0. It's something other than 0. There's some correlation out there. And so the way we determine whether it's a left tail, right tail, or two-tail test is based on the alternative hypothesis. So if this is our alternative hypothesis, what tail would it be? Okay, and you got to look at extreme values on the positive side and on the negative side. What if I was actually testing, my alternative hypothesis is that there's a negative correlation between height and salary. If you measure the correlation between height and salary, you would find it to be something less than 0. You don't know if it would be negative 0.01 or negative 1. You just make the claim that it's less than 0. And so then what tail test would that be?
Left?
Yeah, exactly. The last step in this process would be, what is our observed sample statistic for this hypothesis test in equation form? So what type of statistic are we measuring? Correlation, okay. And so what's the symbol for R? Okay, so it'd be R. We've talked about how you measure correlation. In fact, in the GSS, I think I had you measure correlation for different sets of variables. You would, in GSS, pull up the variable height and the variable income and look at the correlation of that, and that would be your observed sample statistic. Okay, here's another thing. A hypothesis is a claim, and it's a very specific claim. One person had made a claim with like divorce and gender and said that females are able to cope and adjust to divorce better than males based on the variables gender and divorce. So that's a claim, which is a good claim, but our data can't answer that question. The hypothesis has to be reined in to only what your data can answer. A hypothesis isn't evidence. Like I know some people have been saying there's evidence that, or we have evidence that. It's more so you start with a hypothesis, which is just purely a claim that there is no correlation between height and salary. You wouldn't say there's evidence that there's no correlation between height and salary. You just make your claim. And then in the hypothesis test, you gather evidence to see if your claim is a valid claim or not. And probably the best thing is to look at the examples in the book or in the homework solutions just to get familiar with how hypotheses are stated. But probably the best way to think about it is just what's the claim that you're making. If you want to say Duke women's field hockey is better than Carolina women's field hockey, you'd say Duke wins on the road more than Carolina wins on the road. And then those are things you could measure in that way. This is the final session for hypothesis testing. We'll be covering statistical significance, errors, and then significance and sample size. So we went over this yesterday, strength of evidence against the null hypothesis, and that's what the p-value gives us. It gives us the strength of our evidence against the null hypothesis. Can someone give a definition of p-value? Brittany.
The proportion of random sample statistics that are as extreme as the observers.
Okay, and so then as the proportion of randomization sample statistics that are as extreme as our observed sample statistic goes down, what does that tell us? It's sort of like when you do your sampling, you grab your sample of information and you get an observed sample statistic. The question we have to ask ourselves is, this difference or this effect that we're seeing, could that have just happened by random chance? And so the p-value lets you know what's the likelihood that that outcome would have just happened by random chance. The formal decision of a hypothesis test is either we reject the null hypothesis or we do not reject the null hypothesis. You set up an alpha level, which is in this case 0.05, that's the threshold. And actually you do this before you even run your experiment. You just say my significance level is going to be 0.05, and then you run your whole study. At the end you get your p-value, and then you assess your p-value in relationship to whatever your alpha is. So you don't sort of run your whole experiment and get a p-value of 0.08 and you say, I don't know, I think a significance level of 0.1 is good, and this one makes it, so we're going to reject the null hypothesis. Like, that would sort of be cheating. Like if you're practicing taking shots in basketball and you make 6 out of 10 and you're like, I think making 6 out of 10 is good. You know, you'd want to say ahead of time, my goal is to make 70% of my shots, and then you go out and you practice and you tally it up and you realize you only made 60%, you're like, I fell short. It is the more objective way to run the hypothesis test. And so then if it's greater than your threshold, then you don't have sufficient evidence to reject the null hypothesis. So we're going to walk through some examples of where this is. So there's this study about red wine and weight loss, that consumption of red wine is associated with weight loss. So they're trying to tease out the mechanics of what's going on. So RV is an active ingredient in red wine and grapes, and has been shown to promote weight loss in primates. And so a sample of primates had various measurements taken before and after receiving RV supplements for 4 weeks. So they're wanting to see what is it about red wine that's associated with weight loss. So in the test, to see if the mean metabolism rate is higher after treatment, the p-value is 0.013. They're measuring mean metabolism rate before and after. The sample statistic for this hypothesis test is mean metabolism. We have time 1, they check it, and then at time 2, they check it. So then what would be our sample statistic? So it'd be the metabolism rate at time 1 minus the mean metabolism rate at time 2. A lot of times we think, oh, let's look at the difference in means of men and women. You can also look at the difference in means between time 1 and time 2. But it's important to be able to look at a research question or hypothesis test and be like, okay, what is the sample statistic that they're measuring? We know the p-value of the observed sample statistic is 0.013. So then, if they were using an alpha significance level of 0.05, is this difference statistically significant? We have yeses. So the p-value is lower than 0.05, so the results are statistically significant, and we reject the null hypothesis. And this is the formal way to make a formal decision. Reference the significance level, show where the p-value fits in relationship to the significance level, and then make a formal decision. In the test to see if the mean body mass is lower after treatment, the p-value is also 0.013. Using alpha significance level of 0.01, the significance level is sort of like a hard cut point. There isn't like, well, it's close, you know, let's give them a chance. It's this is the cutoff, and if you don't make the cutoff, it's not significant. If you're at the cutoff point, it's not statistically significant. You need to be less than the significance level. The answer would be no. The p-value is not lower than 0.01, so the results are not statistically significant, so we do not reject the null hypothesis. With formal decisions, suppose many researchers around the world are all investigating the same research question, and if the null hypothesis is true using the alpha level of 0.05, what proportion of hypothesis tests will incorrectly reject the null? So what it's saying is, say you're doing these tests and you think that this RV stuff has an effect, but in reality, it doesn't. What proportion of these hypothesis tests will incorrectly reject the null? So we reject the null if the p-value is less than 0.05. Here's our randomization sampling distribution. And this is the distribution of sample statistics that we would get if the null hypothesis was true. These are all the values that could possibly come up. And the chances of a value coming up over here is small, but it's possible. If our observed sample statistic sits somewhere on here on the distribution, we're going to reject the null hypothesis. But what this is saying is that there are some scenarios, very rare, where you would get a sample statistic that's out in this tail if the null hypothesis was true. Most of your statistics are going to be within this range, but on a very rare occasion, it'll be out here. And so your observed sample statistic will be out here, and so you'll say, okay, that's less than 0.05, so we're going to reject the null. But you have to remember that there is a 5% chance that that statistic you got could have been observed by random chance. Rejecting the null is a judgment call. We're 95% confident that the sample statistic would be in this range if there was no effect by the null, but there is a small chance that still there could be.
I understand like the 95 and 5%.
Okay.
I don't understand like falsely negating the null.
5% of the time? If you kind of said we need a p-value of 0.000000001, like way out here, you would never reject the null, because the chance of your observed sample statistic to be that extreme would be pretty rare.
Yes.
So if you want sort of a more strict test and you want to reduce the chance of making an error, what would you do with the significance level? Smaller. Yeah. So if you do drop it to 0.01, you're basically saying, I'm only going to allow myself 1% chance of making an error. There's 4 types of errors that you can make in your hypothesis test, in your formal decision. So up along top here is the decision of either reject the null hypothesis or do not reject the null hypothesis. Is reality that the null hypothesis is actually true, or is reality that the null hypothesis is actually false? We never know this. We just have to make a decision based on our analysis. And so we make our best estimate to either reject the null because we think it's false, or do not reject the null because we don't have enough evidence to say that it's false. If in our formal decision we reject the null hypothesis because the p-value is less than our significance level, but in reality the null hypothesis is actually true, we've made what's called a type 1 error. If our significance level is 0.1, what's our chances of making a type 1 error? So let's say we have a significance level of 0.1, alpha equals 0.1. What's the chance of making a decision to reject the null hypothesis when it's actually true? Brittany?
10%.
So it's 10%. And so a significance level of 0.1 is basically saying here's 90% of the values fit right in here, and if our observed sample statistic is in these tails, we're going to reject the null, but there's a 5% chance and a 5% chance that the sample statistic could be out there even if the null was true, so that makes it a 10% chance that we would falsely reject the null hypothesis. Then this is a decision to not reject the null hypothesis when the null hypothesis is actually false. You can make the error the other way. That's what's called a type 2 error. For me, this is like one of those word puzzles that you have to move around in your head to know what's going on. But actually, by doing this, you'll better understand how this works and how you make formal decisions. So type 1 error is rejecting a true null hypothesis, whereas a type 2 error is failing to reject a false null hypothesis. An example of a type 2 error, let's keep the 90% interval. Where would our observed sample statistic be if the null hypothesis is actually false, but we fail to reject it? The reality is that the null hypothesis is false. There's actually a real difference, a real effect going on. And our observed sample statistic falls right here, and it falls sort of within the 90% interval. And so we can't reject the null hypothesis based on our significance level. But there actually is a significant difference, but the way we set up our test is such that our observed sample statistic falls in a place where we say, nope, we're not going to reject the null hypothesis. I mean, part of that is why you would do multiple tests or multiple studies. So going back to the red wine and weight loss, in the test, alpha equals 0.05 to see if RV is associated with metabolism rate. The p-value was 0.013, and so we rejected the null hypothesis, which claimed that there was no association between RV and metabolism rate. If RV actually is not associated with metabolism, a type 1 error would have been made, and we rejected a true null hypothesis. in a sense, we rejected the null hypothesis, which claimed that there was no association. But if there actually was no association, we would have falsely rejected the null hypothesis. And then to do the flip example, in the test alpha equals 0.01 to see if RV is associated with body mass, the p-value is 0.013, and we did not reject the null hypothesis, which claimed that there was not an association between RV and body mass. If RV actually is associated with body mass, a type 2 error would have been made and we would have failed to reject a false hypothesis. So basically, what this does is take what that table showed and just put it in word form. This is tough because there's a lot of double negatives and stuff like that going on, but it's probably good to just walk yourself through the logic of these. Yes, Brittany?
I had some just getting confused with like the cutoff value. If you run it with 1, you could make no error, but then if you redefine it, it could be a type of error.
Exactly.
So do they ever do that? Like,
yeah.
So like if you go through and you run it with 1 and there's not, do they ever rerun it with less than?
Yeah, the standard is 0.05, and that's fairly consistent. And then people recognize that if 100 people did this study, 5% of them are going to get a type 1 error. But you would also have 95 that have the strong evidence. If someone's doing a study and they pick a 0.1 significance level, you're kind of like, well, you gave yourself a lot of room for error.
So 0.05 is kind of like the extent.
Yeah.
Really accepted.
For social scientists,
Yeah,
but maybe in medicine
medicine,
it'd be different. But you're right, if someone picked a significance level of 0.1, they would make an error, but if someone picked a significance level of 0.05, it wouldn't make the error. Here's an analogy to law of how this works. So in our legal system, a person is innocent until proven guilty. And then the way the court system works is that evidence must be beyond a shadow of a doubt to prove them guilty. So the types of mistakes that you can make in a verdict is convicting an innocent person, so that's equivalent to rejecting a null hypothesis, or releasing a guilty person. The null hypothesis is just not known. And so in a lot of court cases, I'm thinking of like Trayvon Martin in the murder. It's like, I don't know how they're going to decide that case because no one will ever really know it's true. So it's going to be evidence on both sides. There's a good chance of convicting an innocent person. And the other type of mistake is that he's actually guilty, but the jury makes a decision to release him. A person is innocent is basically the null hypothesis, that they didn't do anything. There's no effect, they're innocent. Whereas a person is guilty is our alternative hypothesis. You might think this person is innocent, but I have reason to believe that they're guilty. And so I'm going to propose an alternative scenario that shows that they're actually guilty. And the burden is on me to provide evidence beyond a shadow of a doubt. Not that he's innocent, but that he's guilty. So I need to prove my alternative hypothesis. And so the shadow of a doubt is the significance level. So in a court case, it's a very high threshold that you need to meet to reject the null hypothesis, which says that they're innocent, and determine that they're guilty. Convicting an innocent person, which is basically rejecting the null hypothesis when it's actually true, is the type 1 error. And then releasing a guilty person is a type 2 error, which is the same as not rejecting the null hypothesis. So then, similarly, when there is not enough evidence to convict the defendant, i.e. accept the null hypothesis, the defendant is not declared innocent, it's just declared just not guilty. So you never really say the null hypothesis is true, because that's really not what you were measuring. You were setting up an alternative hypothesis. And so just like in the legal system, they're not going to say Zimmerman is innocent. They're just going to say he's not guilty. Does that help? Continuing on with errors, usually we have no way of knowing whether an error has been made unless we or another researcher conduct another study. It's mainly because we don't know if the null hypothesis is true or false. And the same with like a legal case of Trayvon Martin, where no one will ever know. There's no witnesses, and we only have the one witness, which is the defendant, and it's not good evidence to base solely on one person. who's the defendant. Similarly, we have no way of knowing whether our confidence interval actually contains the true population parameter. Like when we did the Gallup poll, remember how we said the proportion of people who approve of Obama's job as president was 0.49, and then we said a margin of error of plus or minus 0.3 percentage points. We have this distribution and we're 95% confident that the population parameter fits in here, but there's a chance that the actual population parameter fits outside of that. With a 95% confidence interval, 5% of the time, our confidence interval will not contain the true population parameter. Maybe this is the backside of statistics. Statistics sort of make everything look like, wow, like we have proof. We can prove that X, Y, and Z, when in actuality, we just have evidence. And the strength of our evidence is based on our p-value. And so here's maybe an interesting way to look at it. If our observed sample statistic is way out here, what is the p-value for an observed sample statistic that's way out here? It's like 0.00001. If you have a p-value of that, that's basically saying the probability of this outcome happening by chance if the null hypothesis was true is so low that you can say with a very, very high degree of confidence that we have a lot of evidence suggesting that there's a relationship, that there's an effect going on. But if your p-value is 0.05, you're like, yes, we have enough evidence to reject the null hypothesis, but I'm not going to go risk my life on this. Whereas if my p-value is way out here, it's like, I'm pretty confident, because the chance of making a type 1 error is 1/10,000th or whatever. And then going on to significance level, and I think I kind of already addressed this, why would you use a smaller significance level like 0.01? It depends on what claim you're making. And so again, like in certain fields, or even like in the auto industry, they want to know the proportion of parts that have flawed components in it. You know, they're not going to sample every car that they manufacture to see if it has a flaw in it. They sample 1,000 of the cars they produce to see if there's any problems with it. But I bet you their significance level is really, really low because they don't want, by random chance, falsely reject the null hypothesis, that there is actually a flaw in one of the components. So like in the auto industry, the significance level is going to be very, very low because they want to ensure that they're not making a mistake. Whereas, like I said, in social sciences, the threshold is typically 0.05. You lower it to make the test more stringent. Making alpha smaller reduces the likelihood of rejecting the null hypothesis when it's actually true, and the alternative is not true, so making a type 1 error. To kind of bring this back to our samples within social science is that there's a relationship between statistical significance and sample size. So let's say observed sample statistic that we're interested in is the proportion of some categorical variable. And our observed sample statistic is 0.6. Our null hypothesis says, I think the example is flipping a coin. So we flipped a coin 10 times, and McKay guessed correctly 6 out of 10 times. Our observed sample statistic is 0.6. 60% of the time she guessed correctly. And we think that she has some special psychic power because we flipped a 10 and she actually guessed more than what, if she didn't have psychic power, the proportion would be 0.5 because that's, randomly guessing you're going to get it right 0.5 of the time. We think McKay has psychic powers, and so we think her proportion is going to be greater than 0.5. So we're going to test it. As we did, we flipped the coin 10 times, and McKay got 6 of them answered correctly. And it's not statistically significant. The p-value is 0.39, and if our threshold is 0.05, we say we can't reject the null hypothesis. And we say, there's a good chance that McKay, without having psychic powers, could have guessed correctly 6 out of 10 times. And we'd all kind of say, yeah, that's right. There's a good chance of doing that. But if we increase the sample size to 100, what you notice is the distribution becomes more compressed. So this would be 60 out of 100 times she guessed correctly. It's like, what's the probability of that happening by random chance? Well, there's greater evidence that she might actually have psychic powers. And so the explanation for that is that increasing the sample size decreases the standard deviation of the sampling distribution. When you increase the sample size, your sample statistics are going to be more towards the mean value. It reduces the proportion of sample statistics that are as extreme as our observed sample statistic. So if you see like along this x-axis, this goes 0.1, 0.2, 0.3, 0.4, 0.5, and all the way up. And here, when you have a larger sample size, all of the sample statistics become compressed towards the mean or towards the center. And so then your observed sample statistic, which is still 0.6, is pushed out to the tails of the distribution. If you have a sample that's really large, it's easier to obtain significant results. Here's an example how you account for type 2 errors, is that as the sample size decreases, so if you only flip the coin 4 times, the chance of making a type 2 error, of failing to reject the null hypothesis where it is false. So the null hypothesis would be that McKay does not have any psychic powers. And so if we decrease the sample size really low, it becomes harder to get significant results. So say actually that McKay did have psychic powers, but because we only did a sample of 10 coin toss, we can't differentiate that between having real psychic powers and just random chance. Tim, who doesn't have psychic powers, could have guessed 6 correctly. Trying to emphasize the point of you want to have a large sample size versus like taking a really small sample and trying to make conclusions based on that. So failing to get a significant result, okay, so this goes back to the analogy to law. So just because you don't get a significant result doesn't mean that the null hypothesis is true. It just means that we can't reject it. Just like it's not guilty versus saying the person is innocent. And this is particularly true for small sample sizes. Unless the true population parameter is very far from the null value, it's hard to find significant results if the sample size is small. For me, the coin toss thing just kind of makes sense. If, my alternative hypothesis is that McKay has psychic powers, but I only take 4 samples, like I flip the coin 4 times, I'm not going to convince any of you that she has psychic powers, even if she guessed all 4 correctly. There's not enough evidence. So you would say, no. If you want to prove this to me, I want you to flip it 1,000 times. And I want to see that her outcome of successful guesses is significantly different than if she had no psychic powers. So that's just reinforcing the argument that you need a large enough sample size to get significant results. So with small sample sizes, type 2 errors are very likely. When we use the word significance in social science, it has a very specific meaning. There's a difference between statistical significance and practical significance. So just because something is statistically significant, it might not be practically significant. And so with small sample sizes, even large differences or effects may not be statistically significant. And on the flip side, with large sample sizes, even small differences or effects can be statistically significant. A statistically significant result is not always practically significant, especially with large sample sizes. So an example would be, so there's this weight loss program that recruited 10,000 people for a randomized experiment. So 10,000, huge sample size. And then they ran the study and they said a difference in average weight loss of 0.5 pounds was found to be statistically significant. So they took the mean weight of the people in the treatment group and compared it with the mean weight of the people in the non-treatment group. And they found that the difference in mean values was 0.5 pounds. And so that was their observed sample statistic. And when they did the randomization distribution, 0.5 pounds was right here, and it was statistically significant. And it's true, the difference was statistically significant, but it was only 0.5 pounds. So an advertisement could say, we have strong evidence that this weight loss program works. I mean, there's a statistically significant difference in the people who are part of this program and the people who weren't. But you want to read the fine print to see, well, what was the difference in mean values? And you'd read it and you'd say, the significant difference was 0.5 pounds. You'd say, well, that's not going to be worth the hundreds of dollars that I'd spend on this. So you'd ask, is a loss of a half a pound practically significant? Knowing what, when you say significant, what you're saying statistically significant, not necessarily practically significant. Moving on to significance and causation. The p-value alone tells you whether there's a significant association between two variables, but not whether this is a causal association. So even if you have a p-value of 0.00001 of that two variables are correlated with each other, it doesn't necessarily mean that one variable is causing the outcome of another variable. That's all.